Hello, this is Past Paper Guy. I'm going to be solving this GCSE Electronics paper. This is the E1 paper from WJEC, and it's the 2017 paper. As with all papers, I strongly recommend that you give it a go first. I've put a link in the description below, and once you've had a look at that, then you come back and look at this video. Right, so without further ado, let us start. Okay, so question 1a, here's some electronics components list. So it's just simply what are each of these. So this is a buzzer. This is a lamp of some description. And this is a push to brake switch. Okay, the following is a list of different electronic subsystems. I need to put these into here, so we've got to do them all. So a NOT gate is generally considered a process, a latch again, a process, a sound sensor, would be an input, a delay will be some sort of process. A pulse generator, I think that would be an input. Although it could be a process if you hooked it up to something to turn it on and off. A magnetic switch unit, that's in a switch, so that's an input. A motor unit is an output. A lamp unit is an output. And a comparator would be a process. Question 2. Study the following circuit. Okay, so we've got one of these. They always ask a question like this. Select from here the following answer. So what is the value of V2? So V2, if we look here, we want this voltage here. So we start at 0, we need to go to something, and we need to go up by 2 volts to 6. So that's got to be at 4 volts. So we can go up by 2 to get to 6. So that's got to be 0 volt. 0 to 4 gives you 4 volts there. What's the value of I1? I1 is this voltage, this current here. So it comes down here and then splits down there and down there. So if 2 goes down that way and 3 milliamps go that way, and then 5 milliamps must have come that way. What's the value of V3? V3 is here. It's got to be the exact same as V2. So it's 4. And what's the value of I4? Where's I4? This is here. So it's on the same branch as this. So it's still 3 milliamps. Okay, the current coming down there would be 5 milliamps, but it wants the current just there. Right, question 3. Here's a pin out for a logic gate. Write the letter on Q on all output pins. So that's an output pin, that's an output pin, that's an output pin, and that's an output pin, and the outputs of each of the gates there. The symbol plus on the positive supply, that's that. The number's 9 on pin 9, so we start with a notch 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the number 9. What type of logic gate is it? It's an AND gate. Draw the correct logic gate to match the table below. A NOR gate is that one. It's an OR gate with a circle on. A NOT gate is the one with one input. Like so. The following diagram shows a symbol for a transistor. Tick the correctly labelled one. So we've got the collector and the emitter there. We've got the drain and the source there. And here we have, this is off spec now, but it's this one here, that's the cathode and that's the anode. It's like a diode, so cathode and anode on the diode. Okay, the diagram shows a 56 ohm plus 10% resistor. Write down the bands for this resistor. So helps if you learn these off by heart, but we need a 5, 6, and then there are no zeros there. So it's going to be green for the 5. Then the 6 is blue. And then it's got 0 zeros, so it's black. It's there. And then the last band is the silver band, which is already given. The diagram shows a motor. We've got to work out what the power on this motor is. So P, well, we can do P is equal to V squared over R. That is on your formula sheet here on this one. The new formula sheet is slightly different. So we want to do P is equal to 6 squared, so that's 36 divided by R. Oh no, I've done it wrong. I've got the current, so P is equal to IV, so that's equal to 15 times by 6. So 15 times by 6 is that one. So 15 times by 6 is 3090 watts, isn't it? Here is an analog sensing circuit at room temperature. Circle the name of component X. Well, X is a variable resistor. That's the thermistor. V out is 3 volts. So what's the voltage across here? Well, if that's 3 volts, there's 12 of them in total. So that has to be the remaining 9. There. What would happen to the resistance of component Y if an ice cube was placed on top of it? So this is the resistance of a thermistor, and this was with temperature. So if you cooled it down, then you would increase its resistance. So the resistance of component Y would increase. There we go. What would happen to voltage V out in this case? So if this increased here, then this is going to get a bigger share of the voltage, so V out gets bigger and Vx gets smaller. So V out will get bigger. So question 9. Right, so we've got a big question here, 5 marks, lots of reading to do. A luxury car has heated front seats for both the driver and the front passenger. The driver's seat will only operate if the driver is sitting in the seat, the engine ignition is on, the outside temperature is below a set temperature. The passenger seat will only operate if there's someone in the driver's seat. The ignition is on, the outside temperature is there, and there's someone in the passenger seat. So that's basically a copy of all of that, isn't it? So those two are the same. So that signal there and that signal there need to represent those 3 things there. A number of sensing systems are available to use with the following specifications: a light sensor, a temperature sensor, a pressure sensor, and a moisture sensor. Complete the block diagram for the car seat to show the information. So we've got, let's do this part first. So this is going to be the driver here, this is going to be these 3 here, and this is going to be the passenger. So let's do the driver first. The driver is sitting onto the driver's seat, so that's that one. The engine ignition is switched on. So for that, what are we going to use for the engine ignition is switched on? Is that just the switch unit that we're using? I think that's what it's just after there. I think it's wanting that. So we'll put in switch unit. And then we need to detect if it's cold outside. So it says a 1 when it's cold and a 0 when it's warm. So that's the right way around. So a temperature sensor, which must be in here somewhere. There we go. Temperature sensor. And then up here we need a pressure sensor unit for the passenger. close to the edge there. Okay, then over here, before we have a heater, we're always going to need a transducer driver, so that's going to go there. And it's going to go here as well. So that's an easy one. Always before you have a heater, you'll need a transducer driver. And here, we want all three of these things, and we also want this one. So this is going to be another AND gate. Like so. Okay, question 10. Circle the logic gate that has the following truth table. Well, that's an OR gate, isn't it? So there he is. Circle the logic gate that outputs a logical 1 only when both inputs are at logical 1. So that would be, look like that. That's part B. So that is an AND gate. A logic system has the following truth table. Right, so we need to figure out what these are. So here, X is exactly the same as A. So we just need a piece of wire to connect those two together. Y is the opposite of B. If you look there and there, then they are just inversions of one another. So we need a NOT gate to go in there. Oops. And then here, we're looking at this one and this one. And look, it's the same as this. When they're both 0, it's a 0. When any of them are 1, it's a 1. So it's what we called it here, an OR gate. So it's this one. Question 12. So this is NAND equivalence. We need to circle the redundant gates. Right, so it's whenever you have a NOT gate, or a NAND as a NOT gate followed by another one. So that's a NAND as a NOT gate. So there's two there following each other, and there's two here following each other. None of the others. That one doesn't have one before it or after it. Neither does that one. The diagram shows three different combinations of resistors. So we've got to find the values of these. So we've got 23K and then 9.1K. We just need to add those up together. So that's 32.1K. Right, this one, these two are the same, so there's a shortcut here. We can just divide by the number of resistors there are. So that's 56,000 divided by 2 gives you 28,000. So that's 28K. And this one here, we're going to have to use the formula. And the formula for when you've got two resistors is that the total resistance is equal to the product over the sum. So R1, R2 over R1 plus R2. So we will use this, put these values in. So we've got, the fact that they've got K's here doesn't matter. As long as you leave it off all of them, the answer will come out in kiloohms as well. So 7.5 times by 4.8 divided by 7.5 plus 4.8. Okay, so let's try this. 7.5 times by 4.8 divided by bracket 7.5 plus 4.8. Close bracket gives me 2.9 kiloohms, which has to be less than the smallest of those two, which it is. Let's just put the next digit on there, 2.93 to 3SF. Right, now we need to select the truth table that represents this Boolean expression here. So we got A and not B, so A and not B. So we're looking for a line with that one as high, which is this one here. Not A or B. So it's those two. It's going to be a 1 there, a 1 there, or B. It's going to be a 1 there or a 1 there. So it's just this row is 0. So it's this one here. That's the not A, and that's the OR B there and there. Okay, the following shows NAND equivalent circuits for a number of standard gates. So we have to work out what these are. So that's going to be the AND, that's going to be the NOT, and this is the OR, I think, and that's the NOR. You can just double check that. So we've got A and B all knotted, and use De Morgan's theorem on that, and you get A or B. Or you get double knot there and a double knot there, which is equal to A or B. So that's the OR gate, that's the NOR gate. So draw the equivalence. So they even give you the answer. It's nice of them, isn't it? So we just have to copy this into here. And an AND gate is this one here. So it's a NAND gate followed by a NOT gate, and a NOT gate is the only one with just one input there. Question 16. The following circuit is part of a larger electronic system. Input A here needs to be a logical 1 when a switch is pressed. Draw the components that make this happen. So we're going to need a switch connecting it to the positive rail here, and here we need a pull down resistor. Now, what's the purpose of the component labelled Y here? Well, this is a pull up resistor is its name, and the reason it's included is to make B equal to 9 volts when the switch isn't pressed. So to make B equal to 9 volts when the switch S2, this is not pushed. Okay, what combination of switch settings will produce a logical 1 from output Q? Right, so there's quite a bit going on here. So we've got A and B, 0, 0, 0, 1, 1, 0, 1, 1. And this is a NOR gate. So for a NOR gate, we need, this will be a 1, 0, 0, 0. So we need A to be 0 and we need B to be 0 as well in order to get Q as a 1. Right, so to get A as 0, we don't want to push W. So where's switch 1? Oh, you have to include switch 1. So there's switch 1. So we don't want to push that, so that's open. So switch 1 is open there and there, and switch 2 is closed. So it's that one there. Question 17. The following incomplete circuit diagram shows a comparator used to switch on a greenhouse heater when the temperature gets too cold. Okay, so firstly, we are looking at this potential divider here. So V out is equal to V in times by R2 over R1 plus R2. And again, you can cancel the fact that they're all in kiloohms as long as you use everything in kiloohms here, because you've got them on the top and the bottom. So that's equal to 12 volts times by R2, which is that one, 6 over 6 plus that one, 18. So that's 6 over 24. So it is that one there. That's the same. No, it's not. It's that one there. That's the same as that. So now we need to calculate it. So that is 6 over 24, so that's a quarter, isn't it? So it's 3 volts. Complete the circuit to make a non-latching output circuit for the comparator using the components below. Okay, so this is very similar to the 2016 paper. Once again, they don't give you a resistor here. If they don't give you a resistor, that means you can't use NPN transistor. This is a PNP transistor, not on the current spec. Your thyristor, again, not on the current spec. So we have to use the MOSFET. And if we use the MOSFET, we don't need a resistor on its gate, so we can just use a piece of wire there. What modification will be made to the circuit so that the temperature that the heater switches on could be changed? Well, we would need to change one of these for a variable resistor, or we could replace this with a potentiometer. So I'm going to draw on what it is that we would do. So there we go, that's the better solution there. So use a potentiometer instead of the 6K and 18K resistors to get the ref C diagram. Okay, so that means that hopefully the examiner will just look at your diagram and realise that you've done it right and won't even need to read your words. Okay, now we have question 18, last question. A high power LED is used to power as a power indicator. So here we go. What is the voltage drop across R? Well, there's 2 volts there. So then that must mean that there are 7 volts there. So 9 minus 2 is equal to 7. So 7 volts. Select the correct equation to calculate the ideal resistance of R here. So we're going to use R is equal to V over I. We need to use the voltage we just worked out, the voltage across the resistor, 7 divided by, to provide a current of 25 milliamps. So we're going to divide it by 25 and we'll times that by 10 to the minus 3 because it's in milliamps, and that will give us an answer in ohms. So if we get rid of that bit there, we'll get our answer in kilo ohms. So it's 7 divided by 25, which is that one. And now we need to work it out. So 7 divided by 25 is equal to 0.28 kilo ohms. And then we need in ohms, this question is almost exactly the same as last year's paper, just with different numbers. We need to ensure that the current is just less than 25 milliamps. So we must increase the resistance. So 270 is out. So the next highest is 300. So it's 300 ohms. We've got to pick one from the E series there, and we pick the next highest from that. So that is 280 ohms. So that one's wrong, that one's right. And that is that paper. If you look in the description, you will see some links to the paper 2, which we'll be following shortly.